We're technically streaming, but it's just a way of me to get YouTube to do the recording for me so that I don't have to use up hard drive space. But yeah, let's go ahead and look at some problems, shall we?
Can you share the screen?
Yes, yes, of course. Sorry, I had forgotten about that. It'd be better. Let's see, where are we? Um, let's share. Okay, so where are we? Yeah, okay. So first problem. I guess this is question 5. Uh
Yeah.
the homework assignment. John Mass of Belgium managed to move 2 rail cars. Wow. He bit his teeth down the rope and then leaned backwards, pressing his feet against the railway ties. The cars together weighed a lot. What, 800 kilonewtons? Damn. And he pulled with a constant force, 2.5 times his body weight mg, right? Or, if we use just other numbers that are not specific to the problem, maybe just call it 2. At an upward angle of theta, let's just call it 30 degrees. His mass was, let's call it 80 kilograms. And let's say that the displacement was 1 meter. Okay, so neglecting any retarding force from the wheel rotation, find the speed of the cars at the end of the pull. All right. Okie dokie. So I think this problem should just be a fairly straightforward force and kinematics problem. The idea, by the way, can you see my screen?
Yes.
Yeah, so the idea right here is that, okay, it's upwards at some angle, and you don't really care about the, we doesn't seem like we really care about the upwards component at all, right? We only care about the horizontal. The
If,
upwards component would only matter if the wheel was coming up, sorry, if the train was coming off the, coming off the ground, or if we started taking friction into account, because normal force is important to calculate friction. But okay, if all we care about is horizontal, then we just figure that out. The horizontal force by F cosine theta. F cosine theta. Okie dokie. So his own mass, move the cars by 1. Of course. Find the speed of the cars at the end of the pull. So I think his own mass is pretty much just useful to plug that in to get the force.
do we have to change it to regular newtons, or can they stay in?
Sure, let's do that. I guess that just turns into 800,000. It's not super different. But yeah, if we just write F is equal to ma for the rail cars in the horizontal direction, this just turns into 2 mg cos theta, and this is mass of the guy, right? This is mass of the guy. How do I put it? Mass of maybe g for the guy is equal to ma, where this mass is the mass of the train. Yeah, does that seem like all we pretty much need to do?
We just for Excel. No,
Yeah,
no.
and the mass of the train can be figured out because you know the weight of the train, so just use gravity to convert the weight back into mass. And then once you have acceleration, right?
Wait, is
What's up?
mass not the same as weight?
Mass is right. Weight is mass times gravity, right? Remember the
Okay.
whole mass is the same whether you're on the moon or on Earth, but weight is different because you weigh 6 times as much on Earth.
Right, right, right.
Yeah, because gravity is 6 times stronger. But yeah, so all of this simple kinematic equation should let you figure out acceleration. That's your unknown. You can solve for it. Now you know acceleration. And
That's
then,
easy.
what's up?
Nothing. I
Yeah.
went to tutoring from the school,
Uh-huh.
and the guy was trying to tell me that I need to know how to do work, or how to use work to solve this problem.
Yeah, I thought about it for a quick second, and it did seem like work came to mind for a brief moment, but how do you put it? No, it seems like the assumption here is that it's constant constant acceleration seems to be the implication because they're sort of implying constant force as well. In fact, they say constant force. So at this point, just use the kinematic equation, 2a delta x. So v naught squared is 0 because at the start they're at rest. Vf is what we want to find. WTF. And then the acceleration we know and delta x we know, and that's all there is left to say, right? Now to be clear, the tutoring thing, was this like a separate from the class? Was this just like a random help desk?
Yeah, at the library.
Yeah, I if it's a TA that told you this for the specific class, I would probably be a little bit concerned and try to reevaluate what's going on. But if it's like a help desk who's just doing their best to figure things out on the spot, then yeah, I would say they're probably not in the right in this one. You haven't learned about work yet, right?
I haven't learned it, yeah.
Yeah. No, I mean, no, that's all there is to this problem, right? Use Newton's second law in the x direction to figure out what acceleration is and plug that into your handy-dandy kinematic equation. And that's all there is to say.
Sweet.
Simple enough, right? Hopefully nothing too crazy. Yeah, okay. Next one is the tension at which a fishing line snaps is commonly called the line strength. What minimum strength is needed for a line that is to stop a salmon? Wait. Okay, gotcha. So it's just asking, this is kind of like a fancy way of saying basically what is the force or tension needed to stop the salmon?
Okay.
So we're given something. Okay, I'll make up numbers here. Let's say 80 newtons. Let's say 0.15 meters. If the fish is initially drifting horizontally at, say, 3 meters a second. So what minimum strength is needed for... So what's happening here? So basically you have your little fish, and it's sort of going away at 3 meters a second, but it's being hooked by whatever line. Okay. So again, I think this is a situation where the weight is not all that relevant, because I don't think gravity is all that relevant to this problem. It just tells you what the mass of the fish is. All right, that's all that information is needed, I think. Yeah, let me double check that. I don't think gravity is relevant to this one. It's really not telling you what what angle anything is. So I'm assuming the entire problem is just one dimension.
Yeah.
But
it
if
says
this
weight
is,
too, because what you said, weight is equal to mass times gravity, right?
yeah. So like sometimes they just are. Sometimes the weight of the problem is really what the quantity that matters. And sometimes they just give you the weight because they just want to have you jump through an extra hoop to find the mass.
Oh, okay.
You know
So
what I
can
mean?
just solve for mass in this case.
Yeah, that seems to be the case here. But yeah, so what is happening right now is tension. We're trying to figure out the tension that what minimum strength is needed for a line that is to stop a salmon in 14 centimeters. Okay, gotcha. So they tell you the distance over which, and they tell you the initial velocity, right? So this information should let you figure out what the needed required acceleration is. Again, we use our kinematic equation, Vf squared minus V naught squared is equal to 2ax, where delta x is known. That's just the 15 or whatever the displacement is. V naught squared is known. We're given it, and Vf is also known because we're trying to get it to be 0 at the end. So A is the only unknown. So solve for A. So you've solved for A. Now we know A. And now we just plug that into F is equal to ma.
Oh, and then we get the force of the line.
Exactly. So these kinds of problems are, we're sort of noticing a pattern here that these problems are kind of like two-parters, where half of it is kinematics and half of it is Newton's second law. You see that?
Yeah.
The previous problem, also the same, just in the other order. The first half was Newton. The second half was kinematics. And the idea is acceleration is sort of the link between these two, right?
That it's the fact that it's constant throughout the whole thing, right?
Yeah, but like the fact that this acceleration here is exactly the same as this acceleration here. So once you've used one equation to solve for acceleration, then that becomes one of the knowns in the other equation to solve for something else. You see what I'm saying?
Yeah.
It's sort of acceleration. Like, I guess the idea is if you didn't, for this problem, if you didn't first solve for acceleration and try to jump to this equation immediately, you would have been at a loss because you didn't have because acceleration and VF would have been unknown. So you sort of use this equation to find out acceleration first, right? Like, really, that's one way to think about it. The other way of thinking about it is just that these are the two relevant equations, and there are two unknowns, A and VF, two equations, two unknowns, solve. Right? You can think about it either way. For this equation, two equations, two unknowns, which are just acceleration and force, so solve. But because acceleration and force are so similar, for this particular one, I might like to think of it as solving for acceleration first, and then plugging that in to find force.
Okay.
Yeah.
It was
Sorry.
just setting up that
What's up?
the line part was messing me up because I didn't know if it would where it would start. I thought
Yeah.
it would
Okay.
start at 0 and then I didn't know where it would end. But I guess just
Gotcha.
arbitrarily it
Like,
would just
all of that
be
information is sort of encapsulated by the fact that they
yeah.
told you it was 0.15, right? So this is basically equal to delta x, which sort of abstracts out that you don't really need to know the starting and end point in absolute terms. You just need to know the relative distance between start and end.
Right.
That's all. And for this problem, I guess the fundamental idea here is they could have worded this problem a little bit simply and just asked you what force was needed to make this happen, but they wanted to make it a little bit more complicated and talked about this idea of strength and what's the minimum strength needed for this to happen, right? Sometimes physics problems like to do that, where they like to throw in a little bit of garnish into the problem, and I think you just need to get into a good habit of seeing through that and realize that, hey, they're talking about the minimum tension. Really, what they're just talking about is what's the force required here.
Yeah, I just need to do more problems. Get used to it.
It's sort of seeing through some of the little English. Well, I guess I just call it garnish. Is really what it is. Okay, so next one, an elevator cab. Okay, being pulled upwards. The cab and its single occupant have a combined mass of, let's just call it 2,000 kilograms. So M combined. So when that occupant drops a coin, its acceleration relative to the cab is 7.1 downward. Oh, interesting. I haven't thought about these types of problems for a while. Or just like call it 7 meters a second. So acceleration relative is equal to 7.1. What is the tension in the cable?
The fact that it says relative to the cab, does that mean the elevator itself is going down 7 meters per second?
Sorry, I guess I'll change that just to 7. Sorry, what'd you say? Is the elevator going down?
Yeah, it's going down because it says acceleration relative to the cab. So they're trying to say that the cab is going down totally 7 meters. Is that including gravity?
Yeah, I'm trying to piece together this situation right now. So if the elevator was at rest or at a constant speed, right, and you drop the coin, it would be going down at gravity, which is 9.8. But it's going down a little bit lower, and God, it's been a while since I've thought about a constant relative acceleration. But I think you're right. I think the even though the velocity is upwards, I think the acceleration has to be downwards because this thing is smaller than gravity. Does that make sense?
No. Hold on.
No. Yeah, I'm trying
Elevator
to.
cab
What's up?
No, I'm just reading the problem over again.
Yeah, it's been a little while, so my intuition for this is not the best, but I'm gonna write down some equations and hopefully we're gonna make sense of it. Yeah.
Okay.
But what can we fundamentally? What can we say about the situation? Right. It's always a good idea to write, just in the vertical direction, in the y direction. Let's call it. What is F is equal to ma? Right. The sum of all the forces is equal to mass combined times the total acceleration. So acceleration of the elevator. So what's the total forces here? Total forces is tension minus mc times gravity, right? If we just drew a free body diagram, we'd have tension going upwards and then force of gravity going downwards. And for that particular force of gravity, it's m combined times gravity. Yeah, so that's the left-hand side. You agree? That corresponds to sum of forces? All right.
You just subtracted the MC, right?
What's up?
You just subtracted the MCA to the left
Uh,
because the sum is just going to be the
not quite,
tension.
not quite, not quite, because acceleration of elevator is not the same as gravity right now.
Okay.
I'm about to rewrite the right-hand side right here. So mc times a elevator.
Okay, I get you.
Right. So what I'm just a little bit confused right now is I think what they're telling us, the fact that they give us acceleration relative must give us a way to find out acceleration of the elevator. And I think I got my head on a little backwards here at the moment. So how does this work? So acceleration of gravity, which I'm just going to call g, has got to be equal to acceleration of the elevator plus a relative, I guess. Is that right? Yeah, these relative things. It's easy to think about. I find it easy to think about relative velocity and position, but relative acceleration, I gotta give me a second here. What is this saying?
Well, it's still being pulled upward more so than the acceleration downward, so it's got to be overall positive, right?
So acceleration of the elevator, that's not necessarily, well, it could be that it's going upwards, but the acceleration is negative, which means that it's slowing down.
Okay, yeah, you're
Right, that's totally possible. Wait a minute, did I miss this part? It said its acceleration relative to the cab is 70 meters per second downward. Gosh, I've just how do you think about this? Well, it's either got to be plus or minus, right? So maybe you can just try both ways and see which one works. But really, I'd like to screw my head on back straight and figure out what's going on here. So gravity is what would happen if it wasn't acting at all, in which case if it wasn't accelerating at all, if this was 0, right, then a relative would just be equal to gravity, right? Or rather, I should say, instead of if just the elevator wasn't accelerating at all. But if the elevator is accelerating, its acceleration to the cab is downward. Yeah, so what does it mean when this thing is well, hold on, gravity is also negative, right? So gravity is negative, acceleration relative is also downward. Yeah, I mean, let's just plug them in, right? This is just negative 9.8 is equal to a of the elevator minus whatever it is for the problem. What did they say, like 7 meters a second squared?
Yeah.
So then if we just solve for a elevator, I guess that's saying this is equal to minus 2.8 meters a second squared. And what this is saying is that even though it's being moved, the elevator is upwards. The elevator is still moving upwards because the problem tells us. But it's saying that it's decelerating, right? It's like it's coming to the end of its journey and it's slowing down a little bit, which is to say that the force of gravity is a little bit stronger than the force of tension. Yeah. So we take this value. Yeah, it's just, I have a really hard time remembering what the meaning of its acceleration relative to the cab is 7.1. Right? Because let's think about what that means, right? If the cab was totally still and you dropped a coin, it would have a downwards acceleration of minus 9.8, right? But if this value was smaller, like if it was like 7, that means that the elevator has already sort of got a the elevator has already sort of got a little bit of acceleration downwards. Does that make sense? As opposed to upwards?
Why is it going? If the acceleration is going down, then why is that number going down?
Yeah, so like imagine just the difference between the situation where it's 9.8 versus the situation side by side where it's like -7, I suppose. Right? In this situation, the elevator has no net force acting on it. It's not accelerating. It's an inertial frame. It's either constant speed.
Okay.
Whereas this one, the fact that it's -7 rather than g particularly means that the elevator is either accelerating up or down, and we just need to like sort of screw our head on and figure out which direction it is. So if the elevator was being accelerated upwards, you would kind of expect that this thing would be greater than 9.8, right? You see what I mean?
Yeah.
Because if it was like if the elevator was being like, yeah, I mean, you agreed, but just like to verbalize it, it's sort of like if the elevator was already being like pushed upwards, then this value should seem like it has even larger magnitude, right? But it's smaller, so we'd expect it to be the other way around, right? That's sort of like saying the elevator is sort of being pushed away from it. So like this thing it's not accelerating quite as hard compared to the elevator. Sorry. It's a little bit harder to have visual intuition for compared to velocity, but that's the argument. That's the argument. So, okay, that was a very long-winded way of saying we figured out what acceleration of the elevator is, right? It's -2.8 or something like that. So now we know this part. We know this, we know this, we know everything. Now just solve for tension.
Sweet. Then it just becomes algebra.
Yeah. Yeah, no, I'm like 90% confident about that, right? And the 10% chance that I got my directions wrong, well, maybe flip the sign of a elevator. I don't know. But no, I think we should be good. I think we should be good. Let me know if there's any problems solving it that way. But like that's a problem where the signs you got to be really careful about. But like none of the solving is particularly hard, right? It's basically just one equation.
Yeah.
Yeah. Okay, the last one I actually had some other people asking about. And the problem itself isn't too crazy or anything. It's basically saying like there's this cannon which we'll just sort of consider like a ramp, and it's at some angle theta, and they're sort of like accelerating them over some distance, and then they launch, and then they fall down on some net at the same height as the exit of the cannon. So you're given the range. Let's call that delta x. He was propelled inside the barrel to the right for 5.2 meters. I find that language kind of ambiguous, but I think it's saying that the horizontal distance is 5.2 meters. As opposed to the hypotenuse being 5.2 meters. But honestly, the language is just not entirely clear. So, maybe solve it this way, and if it doesn't work, ask a friend to see if the question just meant to interpret it the other way.
Okay.
Do you see what I mean? That I just find it slightly ambiguous?
Yeah, because it could be either or. Yeah.
Yeah, exactly. But, okay, and launched at an angle of 45. So basically, either way, you should be able to figure out the hypotenuse, right? Just by using some trig here.
Yep.
Okay. So then if you also know his mass is, let's call it 80 kilograms, what was the magnitude of the force propelling him? Okay, so again, we have a problem right now that's basically a two-parter. So I'll draw basically the dividing line. Everything to the right here is kinematics. And everything to the left here, well, I guess is a combination of force plus kinematics. But the idea is we kind of want to reverse engineer the problem because we know how far he goes. Delta x is given. And we know the launch angle as well. which means that we can use our two kinematic equations. Delta x is equal to, let's call this, maybe let's call this over here like v naught and t naught. Let's maybe call this point of launch v1 and t1. And maybe let's call the point of landing v2 and t2. But delta x is basically going to be v1 cos theta times t2 minus t1. This is just a very standard kinematic equation, right? And then delta y is going to be equal to 0, is because you're just going up and coming back down, so that net height difference is 0. And that's going to be v1 sine theta, t2 minus t1, minus 1/2 g t2 minus t1. And this should seem pretty standard fare at this point. Because we've got two equations, and we should be able to go ahead and solve for t2 minus t1. Excuse me, hold on. Give me a second. What do we not? We know theta. We don't we know theta. We don't know t2 minus t1, and we don't know v1. So yeah, this is two equations and two unknowns. It should be easy enough to solve, right? Because you can just I don't know, what's the easiest way to do it? You can just maybe eliminate v1 first, or substitute for v1 into the other equation. Solve for t2 minus t1. Maybe we just call that delta t, right? It's just straightforward, right? Just solve.
Yeah, system of equations.
Great. Sorry, I was just saying earlier, because a lot of my other students do struggle with solving system of equations, so I sometimes feel like I need to over-explain. But yeah, system of equations. Now at this point, we solve for v1 and t2 minus t1. But okay, what really mattered here was that we know v1 now. We know v1. That's the really important thing. We know the velocity exiting the cannon, right? So now we can basically forget about everything to the right and just focus right now on the ramp. So if we know that if we know the delta x of the ramp, which is, I guess, the number over here, like 5.2, it's different from the delta x of the travel of the airtime. So if we know the velocity at the end of this and the velocity initial is 0, we can use v1 squared is equal to v naught squared plus 2a times the change in distance, where distance is going to be the hypotenuse, the ramp. I'll just call that d, okay? So we know v naught is 0. We know what v1 is. We know the distance, so now we can find the acceleration. Right? We can solve for that. So far, so good?
Yeah.
That's why I was saying that the first, we reverse engineer the problem to do kinematics, to do the travel time. And then for this part, we used kinematics again to find the acceleration. And now we just need to finish it off by using Newton's second law. But at this point, I remember that some of the other students were actually having a lot of trouble with this problem, because it looked like the solution manuals might have actually been wrong, at least at a glance. But the way I would do this at this point, if I know the acceleration along the ramp, so this is, to be clear, this is along the parallel plane, right? This is basically in the direction parallel to the ramp. But at this point, I would basically say, okay, F is equal to ma for the parallel direction. And okay, what forces are acting on us? The forces acting on us would be the force that's, we're actually trying to find the force of the push or the force of the cannon, plus what is there? Force of gravity parallel. I'll write it out, parallel. And I think that's it, right? Can you think of any other forces? The thing is, one of the forces over here, specifically the normal force, is actually going to be perpendicular just by its nature. So for the parallel direction, you don't have to worry about the perpendicular force, which is really nice. You see what I mean?
Yeah.
Yeah. So I'm pretty sure, unless I'm gravely mistaken, all you need to worry about are the force of the push and the force of the gravity that's parallel. And let me remind you, if gravity goes straight downwards, it's got two components, a perpendicular and a parallel component, right? So if this angle over here is theta, you can convince yourself that this angle over here also has to be theta. And then this is force of gravity. I'm going to use the symbol for perpendicular and use this other symbol for parallel, just like sort of two vertical bars, right? But FG
Mhm.
parallel is just going to be mg sine theta. By the way, do you know why this angle over here is exactly equal to theta?
It's like some weird geometry thing. I don't
Yeah, it
know why,
is.
but I just know where it comes from.
You want me to go over it real quick?
Yes, please.
I think it's good to always have these things down stats so you're not just doing things blind. But yeah, I remember drawing it out. So if you know lots of variable calculus, it's actually really, really clean because you can actually just use the vector projection equation. But if you don't have that offhand, you can always do it with geometry. So if I've drawn this to be perpendicular, right, so this is a right angle, and this right here is parallel to this plane by construction, and this one over here is perpendicular by construction. So what am I doing here? When I'm looking at it, this angle over here has got to be theta, right? Because this is parallel to this, and this line is going through both of them, so that's like a transversal angle. So this is theta. Yeah.
Hold on. I'm still.
You
So
believe
the
me?
bottom one
Yeah. Just you know
is.
how in like geometry, if you had two parallel lines and another line cut through them, then this angle and this angle are the same.
Oh yeah. It's the same
That's
thing.
exactly what's happening here,
Okay.
right? And because this is horizontal, this line and the bottom, and this line is vertical, then this entire angle, it's kind of hard to see. This entire angle is a right angle. So then this one right here is 90 minus theta. 90 minus theta. Sorry, it's kind of hard to see. You with me so far?
Yeah.
And then, okay, well, if this is a right triangle and this is 90 and this is 90 minus theta, then this one has to be theta. That's all.
Sweet.
Yeah, that's all there is to it. Excuse me. So what else is there to say? Okay, this should probably be a negative sign. Because if we define the positive acceleration direction to be over here, this is positive, then this is going to be negative in the parallel direction. You just have to define your convention, right? But the bottom line is that because for the force of gravity, sort of acting against the push upwards, let's choose that to be a negative sign, and let FG itself have positive magnitude, right? Like you can either do this with a positive sign and put the negative sign here, or you can make this positive and make this a negative sign here. It doesn't really matter. You see what I mean?
Yeah.
Yeah. But this is just equal to m times the acceleration that we found from the previous part. Yeah. So at this point, you know everything and just solve. So that's how the problem ought to be done. But and does that make sense to you?
Yeah.
Well, some students were telling me that the solution guide was doing this like wacky thing where instead of doing the nice parallel, instead of trying to do things nicely, and the parallel direction is just so nice, they insisted on setting f is equal to ma for the x and the y directions, which is a huge pain in the ass. It should be doable, but the issue is now instead of drawing your nice force diagram, over here, when we drew things parallel, right? Parallel and perpendicular, we could just ignore the perpendicular component completely because it was irrelevant to the parallel direction, which was the acceleration direction. If you insist, however, on doing things x and y, you can. It's literally possible, right? But okay, what happens? There's a force that's pushing you upwards. Force of gravity is pushing you downwards, and there's a normal force that's pushing perpendicular. Force normal. Right? It's possible if you insist on doing it this way. But okay, what does this look like? This basically means that we have to write down every single x force, which is basically saying F in the x direction. That's this guy. Well, force of gravity has nothing in the x direction, but then you have to subtract out force normal in the x direction is equal to mass times acceleration in the x direction. And similarly in the y direction, now it's just even a bigger pain. You do force of y, force in the y direction, plus force of normal in the y direction, because those two are both kind of positive upwards, minus force of gravity is equal to MAY. And okay, you know AX and you know AY because you know A and the angle, so you can find these through trig. You can find these through trig. You can find the force normal through trig as well. The force normal you should know entirely, right?
It's just the force that's perpendicular to the.
Yeah, actually, hold on. I shouldn't have said that. I should have said that force gravity you know because you have the mass times gravity, right?
Yeah.
And then what else? What else? This is kind of, yeah. I'm trying to remember how to do this exactly. Yeah, it's just so painful when you insist on setting it up this way because really FNX and FNY aren't like. I think they're not really all that different from each other. If you know one, you know the other, right? So they're really not two unknowns, they're just one unknown. And I think the same can be said for f of x and f of y. You see what I mean? It's like there should be some pain in the ass way to solve for this. Like even though this seems like two equations and four unknowns, really it's only two unknowns because they're somehow related to each other.
Right.
Or like really what it is this is just Fn shoot, I don't even know what angle this is, but I think it's theta. Right? Because if this over here is theta, then this is like just opposite angles. So yeah, that's probably a theta. But okay, this is Fn in the x direction, I guess is sine theta this time. And this is Fn cosine theta. And I guess something similar has to be the case for F, right? So this is probably theta. Then Fx is F cosine. And this one is F sine. And oh, look at what a pain in the ass this is, right? A cosine mixed with a sine in kind of opposite ways.
Yeah.
It's solvable. You might have to use like a trigonometric identity or something. But yeah, two unknowns and two equations, it's solvable. But what the students mentioned to me was that their like WebAssign guide or whatever it completely forgot to take force normal into account, which off the top of my head just sounds completely wrong. But they showed it to me, and it just doesn't. It seems like there might actually be a mistake in the in whatever solution they coded up. Because if you want to do this with x and y, you got to think about force normal, right? Because it's literally acting on the system. You can't ignore it. But the answer guide appeared to be ignoring it, or not the answer guide, but like the hint system.
Wouldn't be surprised in this class.
Yeah. So if this question is giving you trouble, maybe save it for last and do the others. You know, maybe. You know, if you're on short notice, maybe just content yourself with taking the L on this one if it's but the point is make sure you know how to do it, and the parallel way is definitely going to be the easiest. But like if that's not giving you the right answer in WebAssign, you know, talk with your friends, and if it's just not working out, it may very well just be that the answer they coded up is bad, and don't take that too hard.
Okay.
Yeah.
And
what's
I'm
up?
a little bit fuzzy on when you say parallel.
Yeah.
Can we just make sure that I know what you're talking about? Because
okay,
right
sure.
now,
Let me elaborate a little bit more. So let's start by talking about x and y because that's easier to visualize, even if it's harder to solve. When I say x and y, I literally just mean like this is x and this is y. Right? We're talking about a 2D system, so we can basically choose any set of orthogonal axes to work in that we want. Right? Yeah. And for this particular one, we just choose the usual Cartesian one that is nice to us because one's horizontal and one's vertical. It just turns out that it's not so easy to solve, even if it's easier to visualize.
Okay.
So with parallel and perpendicular, it's very similar. It's just tilted. The idea now is that instead of working with horizontal and vertical, now we work with parallel, and the usual symbol for this is just two lines. That's parallel, and then there's perpendicular, which kind of looks like an upside down T.
Okay, yeah, okay, I do know what that is. Okay. So for
Gotcha.
us, they just said that they flipped the X and Y to the side and said it was the same flip the axis.
Sorry, what did you say?
For us, we didn't learn it as perpendicular and parallel. We just learned it as somebody took the regular Cartesian coordinates and then turned it a little bit to the left.
Oh, gotcha. Like, did they call it like X prime or Y prime or something like
Yeah.
that? Yeah. Okay. Gotcha. I like these symbols because it reminds me what's going on.
Okay.
But
Just
that's a
okay.
great
I do
clarification.
know what it is. I
Gotcha.
just
That's a great clarification. Yeah. But the basic the underlying principle is that you can set up f is equal to ma for any linear axis. Right. Really, you can even do the vector version of vector f is equal to m times vector a. But to keep things in terms of like very simple algebraic equations, it's nice to think of just f is equal to ma for each parallel for each orthogonal axis. So what I wrote down here was f push minus fg parallel is equal to m times a. And the reason I like to do it this way, because the entire magnitude of a is in the parallel direction, right? The fact that I do it this way means that I don't have to bother with any cosines or sines. With acceleration, I can just write acceleration itself. You see that?
right. Yeah.
Whereas down here, I would have had to do some cosines and sines, and it would have been a huge pain. But apart from that, yeah, like just this problem is so much easier when you choose to do parallel because the perpendicular, the perpendicular direction is totally irrelevant to acceleration, to my understanding.
Yeah.
Right? So this just turns into a single like algebraic equation, and it's beautiful. It's easy to solve. And that's how you would probably do this on a tester quiz.
Yeah,
Unless, of
definitely.
course, their tester quiz also had an error in it.
They had one last week.
Did they confirm it?
Yeah.
That's funny. Were there really students who were getting who got some, full
Yeah.
scores in it
Some
and
people
just
got perfect scores, but nobody had gotten a perfect score before that, so everybody was bugging out.
yeah, how odd, how terribly odd. Yeah, already. So any other questions, or shall we just end it there?
I have some, but I think now that I know how to solve these easy ones, I should probably be good.
Okay, sure. Yeah,
Um,
good.
if you want to end this recording, I have one quick math question.